Welcome back, and if you are coming from part 2 of this series, then it's time to get excited for part 3. We will take our first shear stress work that example. Let's get straight into it. Okay, here we have a 3 meter long wind beam, WB1, and that is primarily resisting lateral wind loads. Okay, wind beams are considered to be as horizontal members located between the upper and lower frames. The load from the wall above and the roof are assumed to be fully supported on the wall below the wind beam. Okay, so we will ignore the dead and live load and just take the wind loads only, and that's what the code recommends to us anyway. WB1 is given to us as 2 beams laminated together. For wind beams, generally speaking, it is probably a better design option to use a single thicker beam rather than laminated beams, especially nail laminated, and I think the code kind of discourages nail laminated. Anyhow, for the sake of this example, we will use screws as our fixing choice for laminating these beams. So we need to work out the size and the spacings of the fixings required to unify this beam in order to transfer the horizontal loads from the wind into the frame. As you can see here, we have a section of the ground floor framing plan showing WB1 in a stair void area, and we have also shown the elevation of the wall framing on the right hand side here. To simplify the structural design model of WB1 into a simply supported beam, some assumptions need to be made according to the Australian standards AS 1720.3, and I think that is under clause 3.5.2.4D. So I highly recommend you, if you are using the Australian standards, then refer back to this clause. Right, the first assumption is the ends of the beam, which are considered to be the main supports, are assumed to be torsionally restrained. So this could be done many ways, such as fix the ends of the beam WB1 onto the wall with an angle. Say we have a 90 millimeter, wide angle to be the width of the wall. So the vertical height of the angle is bolted to the face of WB1, and then the horizontal leg can be bolted onto the top plates of this cross wall here. And I would also make sure that the cross walls are also braced to provide rigidity in the bracing elements. So then we should also be designing the angle as well as the bolts. So that helps the torsional restraint. However, there might be an impractical solution to that, because most of the time the floor joists are running onto this cross wall, parallel to the cross wall. So the floor joist will be in the way of the angle. The other way of restraining this beam torsionally is by extending both sides of the beam, say by 900 millimeters past the void area. Now, when I say 900 millimeters, I mean by 2 joist spacing. Usually the joists are spaced at 450 millimeters. And then what we can do is fix the joist into the face of WB1, say using a seat hanger and some hoop iron strap as well around the beam and the joist, and we can nail that. And this is probably a common way of doing it. Or there's a third way, and we can keep talking about this. And I think that's why I love engineering, because there's so many solutions to one problem. Well, the third way, what we can do is extend the large floor beam B1A right to the cross wall here, cross wall 1, I think I've called it, and then we can fix beams B2A and B3A to B1A as well as WB1. So we can fix that with say triple grips or multi-grip connectors, and of course we need to design for that. So here we have, what we have created here is like a rigid diaphragm for the wind beam to transfer the horizontal forces into the frame when of course taking the wind pressure. Now B2A and B3A, they can also be fixed continuously on the cross walls, which we can screw that from the bottom and from the top plates, okay? And then it will be a good idea to fully brace these cross walls as well to make this bracing element rigid. Now this method is probably a more rigid fixing, which I like, but it's not very practical. Okay, I think extending the beam 900 millimeters or a meter past the void either side and fixing the joist to it is probably a more practical way of doing it. The second assumption, but speaking in general though, I guess at the end of the day, all of these solutions are dependent on the opening size and the value of the pressure as well, and the supporting conditions of WB1. So there's many factors involved. The second assumption is that WB1 between the end supports within this area here is also laterally and torsionally restrained. And this is primarily done by ensuring that the wall below and above are well fixed and restrained. So the roof is well fixed above here onto the wall, and at the bottom, the plates at the bottom should be well fixed into the slab. Look, I would love to talk a lot about wind beams and the behavior of wind beams, but I think I'll leave it to another time. Let's get back to the topic, the shear flow and shear stress. Okay, where are we now? Let's determine the wind loads on WB1. So we are given an N2 wind rating, which corresponds to a gust pressure of 0.41 kPa, which is the serviceability pressure. Now the code allows us to use this value for the member's strength and serviceability when designing for these wind beams. Then we have the pressure coefficient for walls, which is 0.9, and this value is for strength. So yeah, to simply determine the design wind pressure, we multiply 0.41 by 0.9, and that will give us 0.369 kPa. Now we need to determine the effective load width, which is taken by the wind beam. So we have H1, which is the ground floor height, 2740. The floor height is 320 millimeters, and H2, which is the second floor height, is 2590. So the wind in this upper area here is basically taken by the roof, okay? And this lower portion is primarily distributed to this area here and the slab. So yeah, like I said, we must make sure that the bottom plates are also well fixed onto the slab. Now the effective width for WB1 would then be H1 plus the floor height plus H2 divided by 2, and that will give us 2.825 meters. So then the uniform distributed load, WUW, on the wind beam is simply, which is the design pressure multiplied by the effective load width, which would then give us 1.042 kilonewton per meter. Right. Now what we up to? Okay, now this is the beam. Now we'll talk about the beam fixing information that was given to us. The beam size nominated is 290 by 45 F17. Kindling dry hardwood. Number 14 screws with a shank diameter of 6.3 millimeters are proposed. Now the shear capacity given for one screw, which is for one fixings, is 2.4 kilonewton. And this is generally dependent on the joint group, which is JD3, and the load duration factor, K1, is 1 in this case, where dead and live load is 0. And also the depth of penetration into the final member is 35 millimeters. So we're going to be using screws, and that depth into the second member will be a minimum of 35 millimeters. So the question for this presentation is how many screws required to bond the two members, and what spacings of screws required along the length of the beam. And the spacing here is Li, so that's length internally parallel to the parallel to the grains of the timber. Right. Okay, now what are we up to? The beam model, which is simply supported beam with a UDL of 1.042 kilonewton meters. Working out the reactions, we have FYA and the FYB is 1.56 kilonewton. Okay, so what we did is just simply multiply 1.042 times 3 meters, which will give us a virtual point load of 3.12, and then divide that by 2. So the shear force is 1.56 kilonewton. Now we have two, if you remember the two main formulas we need to use for the shear stress and the shear flow. The first step is to work out the shear force, which we have already done, and that was 1.56 kilonewton. For this example, we will be conservative and assume that the shear force is continuous through the beam, such that there is a point load in the middle instead of having a UDL. Now the second step is work out the first moment of area. The first moment of area is simply the sum of A bar multiplied by Y bar. So we need to find the shear stress in this interface here. Therefore, A bar, which is 45 multiplied by 290, and that's 13050 millimeters squared. And Y bar is the distance between the centroid of that hatched area that we need to the centroid, to the geometrical centroid of the whole section. Okay, so in this case, Y bar is 22.5 millimeters. Then the first moment of area will be 13050 multiplied by 22.5. That will give us 293625 millimeter cube. Now, then what we need to determine, the third step is determine the second moment of area. Now, this beam is bending about the minor axis, therefore the second moment of area will be 290 multiplied by d, which is 90 in this case, 90 cubed divided by 12. And that will give us 1.76 times 10 to the power 7 millimeters to the power 4. The fourth step, determine the width of the section where shear stress is considered. Now the width is always, right, the width or the thickness is always perpendicular to the shear stress or to the shear flow. In this case, the shear flow is into the page, okay, between that interface of the two beams. Therefore, the width or thickness is 290 millimeters. The fifth step is determine the shear stress and the shear flow. Now the shear stress, tau, is equal to VQ over IT. Therefore, tau is equal to 1.56, which is the shear force, multiplied by 1,000. We're converting everything into Newton, times 293625. That's the first moment of area, divided by I, multiplied by 290. Okay, and that will give us 0.089 ampere. The shear flow we multiply the shear stress by the width, by 290, therefore, which is equal to VQ over I, and that will give us 26 Newton per millimeter, okay? So this is how much shear flow is traveling throughout the entire beam, 26 Newton per millimeter. And I've done an elevation here showing that the location or that the direction of the shear stress is going longitudinal into the page in this section here. So the beam length is 3 meters, therefore the total longitudinal shear force will then be 3,000 multiplied by 26, and that will give us 78,000 Newton, which is equivalent to 78 kilonewton. So that's one shear force that is traveling through the entire beam, longitudinal shear force. Therefore, we need to distribute the screws in the entire beam to withstand 78 kilonewton. Okay, and then the final step, step 6, the number of screws required to bond the members together. Now say we use 4 rows of screws across the grain, so 2 rows either side staggered, and the screws are 80 millimeters long, which means they penetrate 35 millimeters into the final member. I think the Australian framing code AS 1684.1 requires a minimum 75% of penetration depth into the final member. So depending on which country you're from, I urge you to check the requirements of your code. And then we also need to check the edge and internal distance as per the codes as well. So again, the Australian code shows all the requirements for the edge, internal, and end distances. From memory, I think it's table 4.8, but don't quote me on that. Please check it. It gives like some information about the edge distance that we must maintain. The minimum depth of the edge distance is 5 times D, where D is the screw shank diameter. And I think the minimum distance across the grain is 3D, 3 times D. And along the length of the grain is 10D. So yeah, to double check that as well. Where are we? So going back to our problem, we need now to work out the capacity of one screw. So we know that the capacity of one screw is given to us as 2.4 kilonewton, okay? So we have 78 kilonewton throughout the longitudinal shear force, and we have 4 rows proposed. So 78 divided by 4, that will give us 19.5 kilonewton per row, which means all the screws in every row have to take 19.5 kilonewton. Therefore, yeah, we need 19.5 divided by 2.4. We need 8 screws for each row. Hope that all makes sense. So Li, which is the distance internally along the grains, would simply be 3 meters, 3,000 divided by 8, and that will be 375 millimeter centers. Okay. And I think AS 1684 gives us a maximum value for the centers. It's 2 times the beam depth. Okay, so in this case it would be 2 times 290, which is more than sufficient here that we have. So 375 centers is acceptable. So yeah, so now we can adopt 4 number 14 screws, 6.3 millimeter shank diameter at 375 centers along the length of the beam. Now if you go up a screw, like say 4 number 18, I think the second one, the one above that is number 18, and I think it's 7 millimeters or so the diameter, we might be at 400 centers. However, check if you're using the one above that, then check the edge distances and the requirements for that. One thing you need to be aware of is that we designed the spacings and the number of fixings based on the maximum vertical shear force, which is basically at the ends of the beam. So this is a very conservative design. The shear force for a beam with a UDL reduces linearly until it becomes zero in the center. So in reality, we will not get 78 kilonewton longitudinal shear force throughout the length of the beam. We could probably take the average value of the shear flow to space out the rest of the screws. So yeah, at the ends of the beam, we can place maybe extra screws, do it at 375 spacings, and then as we move towards the center of the beam, we can space it at a much larger spacings. Wow, I think that presentation went on for a bit, but I hope that you guys have benefit from it. So yeah, in the next video, we will look at a 2100 millimeters long beam, B1, supporting roof and floor loads. There is a 45 millimeter overhang issue that we had, and we need to fix the situation by providing B1A to externally, fixing it to B1. So we need to work out the size and the spacings of the fixings. Yeah, so please stay tuned. In the meantime, if you have enjoyed this video and found it useful, please like, share, and subscribe so that others may also learn. Until next time, we hope you have a great afternoon.